Close your eyes and picture an airplane. You're probably imagining a long cylindrical tube with wings jutting out from the sides, engines slung beneath those wings, and a tail fin rising from the rear. That image has defined commercial aviation for nearly a century, an iconic silhouette that's become synonymous with air travel itself. But what if everything we thought we knew about aircraft design was about to change? What if the airplanes of tomorrow looked nothing like the jets we see today? Enter the Flying V, an aircraft so radical in its conception that it seems ripped from the pages of science fiction. This isn't some distant fantasy dreamed up by Hollywood designers. It's a serious engineering project backed by one of the world's leading airlines and one of Europe's most prestigious technical universities. The Flying V doesn't just look different, it represents a fundamental reimagining of how we think about flight itself, challenging assumptions that have governed aircraft design since the dawn of the jet age. The story of the Flying V begins in 2019, when Dutch airline KLM and researchers at Delft University of Technology unveiled their vision for the future of aviation. Their proposal was audacious in its simplicity, yet revolutionary in its implications. What if the fuselage, wings, and tail could be merged into a single, continuous, V-shaped structure? Traditional aircraft separate these elements into distinct components: a tube for passengers and cargo, wings for lift, a tail for stability. The Flying V throws that convention out the window, literally integrating everything into the wings themselves. Passengers, cargo, fuel tanks, and all the systems needed to keep an airplane flying would be housed within a giant V-shaped lifting body. From above, the Flying V resembles an enormous boomerang slicing through the sky, its sleek profile tapering from a wide central section to narrow wingtips. The engines, rather than hanging beneath the wings, as we're accustomed to seeing, are mounted at the rear of the V's arms. The nose is flattened and broad, and the passenger cabin follows the contour of the wing roots, creating an interior space unlike anything in commercial aviation today. This isn't merely an aesthetic exercise or a designer's flight of fancy. Every aspect of this unconventional shape serves a specific aerodynamic purpose, addressing one of aviation's most persistent challenges: efficiency. Traditional aircraft designs waste an enormous amount of energy. The cylindrical fuselage, that familiar tube we all board when we fly, is actually an aerodynamic liability. It creates drag without generating any lift, essentially being pulled through the air by the wings without contributing to the airplane's ability to stay aloft. It's dead weight from an aerodynamic perspective, a necessary evil in conventional designs. The Flying V eliminates this inefficiency by making everything contribute to lift. Every square inch of the aircraft's surface helps keep it in the air. The result, according to KLM's extensive research and computer modeling, is staggering. A potential reduction in fuel consumption of 20% compared to a similarly sized Boeing 777. In an industry where fuel can account for 30 to 40% of an airline's operating costs and where profit margins are often measured in single digits, that kind of efficiency gain isn't just impressive, it's potentially transformative. Let's delve into the specifics of what makes the Flying V tick. The aircraft is designed to carry approximately 314 passengers, putting it in the same capacity class as the Boeing 777, one of the world's most successful wide-body airliners. Its range of 4,000 nautical miles makes it suitable for most long-haul routes, from transatlantic crossings to flights across the continental United States, or between European and Middle Eastern cities. The cabin width varies across the V shape, wider at the root, where the two arms meet and tapering toward the tips. This creates some interesting possibilities for cabin layout and passenger seating that differ dramatically from what travelers experience today. The engines represent another departure from convention: high bypass turbofans, the same type that power modern jetliners, are positioned at the rear of the V's arms. This placement isn't arbitrary, it offers multiple advantages. First, it significantly reduces cabin noise. In traditional aircraft, engines mounted under the wings are positioned close to the passenger cabin, and despite extensive soundproofing, engine noise remains a constant presence during flight. By pushing the engines to the rear, the Flying V puts maximum distance between the noise source and passengers' ears. Second, the rear-mounted configuration optimizes airflow over the lifting surfaces. The engines don't disrupt the smooth flow of air over the wings because they're positioned downstream, behind the main lifting area. This contributes to the aircraft's exceptional aerodynamic efficiency. The integration of fuselage and wings creates benefits that extend beyond simple drag reduction. In conventional aircraft, fuel is stored in the wings, and the weight of that fuel creates bending moments, forces that try to flex the wings upward and downward during flight. These forces require strong and therefore heavy wing structures to resist them. The Flying V distributes fuel tanks across both the wings and the central fuselage area, creating a more balanced mass distribution. This balanced loading reduces the structural stresses on the wings, which means lighter structures can be employed without compromising safety. Lighter structures mean less weight to carry, which means less fuel needed, which means even more efficiency gains. It's a virtuous cycle of engineering optimization. Even the tail configuration breaks with tradition. Instead of the familiar vertical stabilizer rising from the rear fuselage, the Flying V employs a small T-tail positioned at the apex of the V shape. This provides yaw stability, the ability to resist unwanted side-to-side motion while minimizing drag. More importantly, because the entire structure generates lift rather than just the wings, the Flying V produces more lift per unit of wing area than conventional designs. This has practical implications. The aircraft could potentially operate from shorter runways, or it could carry heavier payloads over the same distances. The blending of lift-generating surfaces with the passenger and cargo compartments represents a fundamental shift in aircraft design philosophy. Inside the Flying V, the experience would be distinctly different from conventional air travel, yet designers have worked hard to ensure that different doesn't mean uncomfortable. The passenger cabin occupies the central portion of the V shape, measuring roughly 10 to 12 feet wide at its widest point. Seating is arranged in a 2-2-2 configuration, and here's something remarkable. Every passenger could potentially have a window seat. The V shape naturally creates more exterior surface area per passenger than a cylindrical fuselage, and the cabin's slight slope actually makes the space feel more open and less claustrophobic than traditional tube cabins. The rear-mounted engines deliver on their promise of reduced noise, creating a remarkably quiet cabin environment. Imagine crossing the Atlantic in near silence, able to hold a normal conversation without raising your voice, without the constant background drone that characterizes long-haul flights today. Lighting, ventilation systems, and emergency evacuation procedures have all been meticulously modeled in computer simulations to ensure they meet stringent safety regulations despite the unconventional layout. Engineers have had to rethink emergency exits, evacuation slides, and passenger flow, but solutions exist for all these challenges. Cargo holds are positioned in the lower sections of the wings, directly beneath the passenger cabin. This arrangement improves the aircraft's balance and center of gravity while allowing for faster loading and unloading operations. In terms of service, airlines could theoretically adapt existing Boeing 777 type catering and maintenance procedures to the Flying V, reducing operational learning curves. It's a design that combines radical aerodynamics with practical airline operations, a rare feat in aviation innovation. The economic case for the Flying V is compelling and extends far beyond the headline-grabbing 20% fuel savings. A typical Boeing 777 burns approximately 6.8 metric tons of fuel per hour, though this varies depending on payload and distance. The Flying V's integrated design and optimized aerodynamics promise a fuel burn reduction of up to 20%. That's a massive reduction when multiplied over thousands of flights per year. Fewer emissions, lower operational costs, and better range efficiency make this aircraft highly attractive in a world increasingly focused on sustainability. Aviation is responsible for about 2 to 3% of global carbon dioxide emissions, and airlines are under increasing pressure from regulators, environmentally conscious passengers, and their own corporate sustainability goals to reduce their carbon footprint. Concepts like the flying V represent a shift in thinking. It's not just about moving passengers from point A to point B, but doing so more efficiently and responsibly. In addition, the flying V's weight distribution and wing structure reduce wing bending and torsional loads, which means structural efficiency is higher. Less material is required to achieve the same strength, reducing manufacturing energy use and potentially lowering overall aircraft weight by 15 to 20% compared to traditional designs. This has ripple effects across maintenance costs, fuel consumption, and overall airline profitability. The blended wing design creates unique flight characteristics. The aircraft is inherently more stable in pitch because the lifting surfaces are continuous. Lift is generated along the entire structure, so stall behavior is different from traditional tube and wing aircraft. Simulations show that the flying V can maintain smoother flight in turbulence, with reduced wing flex and lower overall aerodynamic drag. Landing and takeoff are also slightly unconventional. The central V configuration requires precise angle of attack management to ensure all three main points of the V touch down properly during landing. Engineers have been experimenting with high-lift devices and advanced flap systems to maintain controllability at low speeds. Takeoff distances are comparable to a Boeing 777, but simulations indicate potential for slightly shorter roll distances due to improved lift characteristics. Another fascinating aspect is yaw and roll control. With engines mounted at the rear, differential thrust can assist in turning the aircraft, reducing the reliance on traditional rudder inputs. Combined with small T-tail surfaces and advanced fly-by-wire systems, pilots can achieve excellent maneuverability while maintaining aerodynamic efficiency. The aircraft would essentially fly itself differently than anything pilots are currently trained on, requiring new certification standards and comprehensive training programs that would need to be developed from scratch. Of course, no revolutionary aircraft concept is without challenges. First, the unconventional shape poses certification hurdles. Civil aviation authorities like EASA and FAA have decades of experience with tube and wing designs. Their certification standards, testing protocols, and safety requirements are all built around conventional aircraft configurations. Convincing regulators that the flying V is safe in all conditions, from engine-out scenarios to emergency evacuations, will take extensive testing and flight data. This process could easily take a decade or more and require billions of dollars in investment. Second, airport infrastructure is designed for conventional fuselages. Boarding bridges, ground handling equipment, and cargo loaders would need modifications to accommodate the V-shaped layout. While not impossible, these adaptations represent upfront costs airlines may hesitate to absorb unless the fuel savings and operational efficiency justify the investment. Smaller regional airports might struggle to make these modifications, potentially limiting where the flying V could initially operate. Additionally, passenger psychology could be a hurdle. Humans are used to the cylindrical fuselage cabin experience. Some may feel uneasy with a V-shaped cabin, especially in the upper portions of the slope where the cabin narrows. Airlines would need to invest in cabin design, seating, and lighting to make the interior feel familiar and comfortable. The first few years of operation would be critical in establishing passenger confidence in this new design. Finally, maintenance crews would require specialized training to handle systems distributed across the V-shaped wings. Fuel lines, control surfaces, and structural components differ from traditional aircraft, meaning new maintenance protocols would be essential. This represents a significant training investment for airlines and could slow initial adoption rates. Despite these challenges, flying V represents the future of aviation. Think of it as a bridge between conventional jets and ultra-efficient blended wing body aircraft. By integrating fuselage, wings, and fuel systems into one coherent structure, it provides a glimpse of what the next generation of airliners could look like. KLM has indicated that the flying V is designed to accommodate biofuels or even hydrogen in the future. Combined with its aerodynamic efficiency, this could make long-haul flights dramatically more sustainable. The Flying V may not be in service yet, but it offers a tantalizing vision of the future of aviation. With its V-shaped design, rear-mounted engines, integrated fuselage and wings, and potential for massive fuel savings, it challenges everything we thought we knew about aircraft design. The skies of tomorrow may look very different, and that difference might take the shape of a giant V cutting through the clouds, carrying passengers more efficiently and sustainably than ever before imagined.